Good evening, everyone, and thank you very much for coming. And it's a real honor to give a talk in front of all of you. I'm going to talk about almost my entire career in the research of wireless communications. It's almost spanning 20 years under the title of From the Big Bang to Wireless Communications and Beyond. So when we're talking about wireless communication, we cannot forget two major historical milestones. The first one is the proof of existence of electromagnetic waves using Maxwell equations. The genius physicist James Clerk Maxwell is indeed from Edinburgh, Scotland, so that's another landmark historical milestone for Scotland, indeed. And the second one, once electromagnetic waves is proved, to bring it to practice, all the engineering work was done by Galileo Marconi, who actually invented the radio communications, and he actually proved to send some radio signals over a mile and then over across the Atlantic in 1901. The engineer Marconi also discovered shortwave radio, and then the technology was enabled by his inventions until 1945. Before 1945, most of this technological development regarding wireless communications was focused on World War II and communication between key people. But after the World War II, the Bell Systems lab in USA started to realize that they can actually make telecommunication system for civilization. So that started in 1945. And since then, we have gone through many generations of wireless communications. Indeed, in the earlier days, the most challenge that they faced was doing telecommunication network that can actually transmit signal over longer distance for voice in particular. And eventually, the analog communication system that was developed by Marconi and Dole was changed to digital era. There will be digital communication system from second generation, but it took almost like 40 years to move from analog communication to digital era. And since then, the communication started to grow significantly. It's almost grown exponentially. So we have come to 2020 now. We have passed fourth generation, and we are starting the fifth generation of communications, which is a very exciting time for not only for the researchers and scientists, but also for users, because indeed the fourth generation had brought lots of people-to-people communication and also the internet. People were using internet, and we were experiencing communicating anywhere, anytime. So that was the motto initially, but now for the fifth generation, it's changing to from people communication to device communications. And also there is a new thing, it is more or less not new, it's already started exploited, the edge cloud computing. In the sense the devices are going to communicate between them and also going to communicate to the cloud. And because one of the major bottlenecks that we were facing all this time is putting a lot of computational complexity in the small devices and smartphones. So using this cloud computing, we can actually offload a lot of the computational power to the cloud and do most of the computing in the cloud to bring more intelligence to devices. So since World War II ended, now 75 years, we have been moving in the telecommunication revolution. It's also called digital revolution, and now we are meeting in the intelligent data era. So both together, it's bringing a lot of exciting opportunities, in particular to bring more advanced solution for the society, in the sense people are talking about smart and autonomous vehicles, and healthcare can be improved using smart healthcare devices and smart homes and so on. So it's going to be, the fifth generation is more like device-to-device communication domain. So my research more or less focused on from third generation to fifth generation, and I'm going to talk about my research embedded within the 75 years of history of the digital revolutions. So before I start my research, Indeed, I would like to thank to my mentors. I was really lucky enough to have very pioneering mentors in my life, in my early career. So started my PhD with Professor Simon Heckin, who was a pioneering researcher and a pioneering textbook writer. And also I was really, really fortunate enough to go and work with Bell Labs, where most of the innovation happened with some of the pioneering researchers like Jerry Fauchini and Ronaldo Valenzuela, who invented something called multiple input, multiple output communication, which actually founded the fourth generation and fifth generation foundation for the fourth generation, fifth generation wireless communications. And my luck didn't stop at that point. After I finished my PhD, I also went to work in the Industry Canada. It's called Communication Research Center with another pioneering researcher, Dr. John Lodge, who was part of the inventing team of the Turbocode, which is another milestone in the history of 75 years of wireless communication revolution. And finally, I'd like to thank Professor Jonathan Chambers, who was my first mentor in UK when I moved as an academic to UK. Without his support, I could not have made up to this point. So I'd like to thank, and also before I go into my talk, I think I'd like to thank to all my collaborators and my PhD students and researchers who supported the development of this talk. So I would like to thank them as well. And then, so rather than putting an outline of the talk, I prepared this slide. And so what I did in the slide is I have my 20 years of history from 1999 when I started my PhD. My work in wireless communication became much more exciting for me because I had the opportunity to go and work with Bell Labs in 1999, where most of the invention, the history of telecommunication digital revolution happened. And over the 20 years, I'm still working with them, and even in 2019, one of my PhD students was able to go and work in the labs, in the same lab. It's the Crawford Hill lab. And on the top of these slides, I have some of the major invention happened in the Crawford Hills lab. Just showing up when Marconi started doing telecommunication over Atlantic. After a few decades, the Crawford Hill lab was able to communicate to the space using their pioneering inventions. So my talk is going to start from 1945, just after the World War II till now. So the first invention that I would like to mention from the Bell Lab is the transistors. So without making this transistor, we could not have amplified signals. And these are the nerve system of any circuits now for us to achieve the fifth generation wireless communication from them. So that was the first invention. And the other one is, I would like to mention about the first, so this is called Diana antenna. Here it was used in the World War II for detecting enemy targets. And then they upgraded it using 8x8 arrays radar, made it as an 8x8 array radar. And then indeed they measured signal bouncing off from moon. So it's like 238,000 miles away. So this is the transmitter signal. This is what they receive after 2.5 seconds. So that one is another milestone. That was a milestone. That's the first time ever in the history people managed to communicate to something extraterrestrial, to the space. So, and the other one is the Telstar. That's the first satellite built in US. That was also happened in that lab. And finally, the Big Bang. So this horn antenna was built by the same lab in 1964, and they intended to measure satellite signals and detect satellites, but accidentally they actually measured the Big Bang, the electromagnetic signals radiated from the universe during the Big Bang time. So they managed to measure it. I think you can hear or look at this history in the internet as well, and this is the sound they recorded. This is the electromagnetic signal they received, made it as a sound signal. So the whole history was built in that. So in this time, some of this, the lab is now closing down after all this historical milestone was achieved. Actually, the Crawford Hill lab is closing in this April. So I thought of putting this historical landmark in my talk. So that's the sound from Big Bang that they recorded. So now I'm moving into my talk. In the sense, my work is mostly focused on physical layer and indeed some sort of coding modulation designs as well. So the pioneering invention happened, it is also called information age. It was invented by Claude Shannon. He was also located in Bell System Labs. So most of the pioneering work happened in the same location in US. So he not only invented the digital communications, so the digital communication revolution is same as the telecommunication revolution, because the digital communication is the one let us actually communicate far distances. So he not only the pioneer for digital communication, I also recently got to know he was a pioneer person for artificial intelligence as well, because in early days he even developed devices that can learn and remember things. And it is important to mention now, because we all, in the 5th generation and the beyond generation, we're also thinking about intelligent devices and intelligent smartphones and so on. So he was the pioneering for all of this. In particular, what happened is in 1945, when the Bell Systems Lab decided to make telecommunication network for civilization, one other thing happened is it's very difficult to transmit analog signal for far distances. So eventually they started to realize that they cannot just send analog signal and then amplify again and send it again and again and again. What happens is when you send analog signal, the analog signal can be any form of analog signal. It can be voice. So I just put a sine wave here, but actually, okay, sine wave here, but actually it can be any form of analog wave. What happens is when you transmit for far distances, the power will go down, and then at the receiving end you get some noise and some impurities, and then what happens is if you amplify the signal, then noise and impurities will get amplified, and after a certain level of transmission, we will lose the complete signal, or we get very distorted signal. So people started to realize the analog is not going to go further, but a lot of the people were working on improving the analog signal transmission. Claude Shannon started to think about how he can actually change the form of transmission. In the sense, he started to think what we are transmitting is information. We are not transmitting the analog signal. So if we can extract the information of the signal, it can be any form. It can be video, data, or voice. If you can extract the information in the signal, and then if you can code that like a bit, a binary, ones and zero, then we can transmit. And if you can regenerate the signal before it completely dies away, so before it becomes very, very small, then we can actually exactly reconstruct the signal. So we're not stuck with the analog form, which we can just 1 and 0, so we send it and we repeat it, and we can repeat again and again. So that's the fundamental Shannon thought in mid-1940s. And then so what we will do is, rather than sending analog signal, we can send 1 and 0s. So indeed, that was the major innovation that brought us to this day. And if we have never realized that we can do digital form of communication, we don't know where we would have been. So Shannon is named as father of information age, not because of the digital communication invention, but also he has done many steps that led to digital communication. So in his master thesis, he is the one who invented the digital logic machines like O, and not from the Boolean algebra. So that's the foundation for digital computers. And he also worked during World War II time in the cryptography, and he actually wrote a paper called Communication Theory of Secrecy Systems, and that founded the modern cryptography. And then when after the World War II ended, then the Bell Systems Lab was thinking about digital communication for everybody. He invented the mathematical theory of digital communications. So that was the magical start for the digital era. It's not only for communication, it is also for any form of digital storage and everything. So just thought of mentioning his wife, Betty Shannon as well. So that time of the era, it is not very common for a woman to work as a technical member of staff. She was a genius mathematician, and she was a collaborator with Claude Shannon throughout his invention and the career. So I thought of mentioning her as well. And yeah, so Shannon has invented the bit and the information theory. The next step was the Bell System Lab was trying to actually develop digital system, but that was in 1946. And we didn't get the digital communication for another 35 or 40 years, so there's a long, complete form of some parts of the communication system was changed to digital, but not completely. So there are many theorems came out of Shannon in combination with his colleagues. One of them is Nyquist-Shannon theorem, because Nyquist has been working on sampling theorem even before Shannon came up with the bits and the information theory. So together with the Nyquist, they have actually identified how they can actually sample, how fast they have to sample any signal. So they have identified the rate that they have to sample. And the other thing is you have to quantize the signals to bring bits. So Shannon also brought up the rate distortion theory, which actually said, how can we manage the distortions to the level that we want it. And then it is binary. So this is a simple procedure at that time. And then Shannon didn't stop at that point. Shannon also, with one of his colleagues, has drawn how the communication system is going to be. So according to him, so we make ones and zeros. So one other thing is when you go from analog signal to digital signal, you increase the bandwidth. So you need more bandwidth to transmit the same signal. So Shannon recognized that sometimes when we digitize this, we get some redundant bit. We can actually compress the bits. So he actually devised a theorem for source coding. So he said, like, we can compress the data, and then when we transmit it, it can flip, and you get errors at the receiving end. So you don't exactly get what you want to get. So Shannon also said you can actually introduce channel coding. So you introduce redundancy bits such a way that you can actually correct errors. And then modulation and the channel, and then it was the theorem he wrote in his paper, his famous paper. And then the most popular theorem, at least in my research direction, was Shannon's capacity limits. He didn't stop at the point. He also said how fast we can transmit, how many bits per second that we can transmit over a channel if you know some of the channel properties and the bandwidth and the noise that we are facing. So it's a very simple formula. It's B log 2 1 plus SNR bits per second. So that's become one of the famous formula, and that gave a lot of insight until now for people who are designing communication systems. So in this, we know this rate. It's like Shannon said, this rate, we cannot, it's almost like how Einstein said, you cannot travel faster than light, but Einstein didn't give any sort of way to travel up to the speed of light. The same way Shannon said, okay, this is the maximum rate that you can transmit, but Shannon never said how you can actually transmit, how you actually code to transmit at this rate. So he actually proved the existence of the code, but he never gave the coding. Another thing is how we can increase the capacity. Some insight, you can increase the SNR. Okay, if you increase the transmit power, we can increase the rate, but that's going within the log. So in order to increase one extra bit, we have to double the transmit power. And if you want to increase the 10 extra bit, we have to increase the power by 1,000 times or something like that. So it is really hard to increase the capacity of a channel by increasing SNRs to increase double or multiple times is really difficult. And the other thing is you can increase the data rate by increasing the bandwidth, but the problem with that is the bandwidth is connected to sampling rate. So if you increase a huge bandwidth, then you have to have a really good analog to digital converters as well. So these insights were really helpful. So the challenge put for the engineers is how to achieve this capacity without making an error at the receiving end. So you can actually, so even though Shannon said this theorem, he never provided a coding design. But indeed, he said a long random coding technique exists that can actually give you very arbitrarily low error rate at the receiving end. So that's what Shannon said. But since then, for many decades, almost 30, 40 decades, people have been working various different coding, because Shannon gave many theorems like compression theorem, error control, cryptography, and modulation. So there's so much of research went on that. And finally, only in 1993, the long random codes were invented. They were called turbocodes. So that went into the third generation, fourth generation standard. In the sense, you can question why is it difficult to get random code, a long random code. You just take a random code. The main problem with the random coding is not that issue, but decoding at the receiving end of that random code is extremely difficult unless we have some sort of special design. So the Turbocode team, so it was invented in France. It's a team of French people, and as I said, Dr. John Loach was with that team when they invented this code. So this is sort of a random code they invented called Turbocode. The randomness comes from this random interleaver. So ideally, we cannot have random interleaver. We should have a pseudo-random. So we had to design, because the receiver should know what randomness we put there. So we cannot just generate random every time. If you generate every time a randomness, we need to have a way to transmit the random interleaver to the receiver, because the receiver is going to involve the randomness. So the main invention of this code comes from the decoding, because usually the maximum likelihood decoding, that's the famous decoding, is used for decoding, which is very difficult for long codes and particular random codes. So if you do some algebraic code, that was the history before the turbo codes. People were designing sort of algebraic codes that they have maximum likelihood decoder available for those shorter codes. So these ones are longer code, so we cannot do maximum likelihood. So the thing they did is it's sort of a turbo decoder in the sense it's used the turbo engine principle in the sense it's used the exhaust to pump up the machine. So it is using some sort of thing that we would have thrown out in the conventional way was used to derive a maximum likelihood decoder in an iterative manner. So it's an iterative decoder, so you do slowly decode the final coding. So that's main. So how I involved in this, because as I said, John Loach, I went to work with him. So in the sense, this plot is showing the importance of Turbocode in the sense, so this is the SNR. So 14 dB SNR means you had to have so much of signal power given to that. This axis shows the error probability, okay. So going down means it's much more reliable. So we want something very closer to Shannon capacity limit. So according for this code, Shannon said you can actually achieve arbitrarily low error close to 0 dB. That's what Shannon said. But if you don't encode anything, it was like 14 dB away from where Shannon was. The convolutional code, that was one of the conventional code, that was about 8 dB away from Shannon limit. That was the one used in earlier 3G standards, and also deep space communication, satellite communications. And then this is the results that Turbocode was providing, and this one was the original results by the French. And then the problem was there is error flows starting early on. So eventually JPL, because these satellite communications need really good code, because it's deep space, you're transmitting far away, your receive power is going to be very low. So you need to have really, really good codes to actually decode anything in the satellite communication. So JPL and NASA was very keen, they did that. I was with CRC, and then we did some interleavers, random codes and decoders that achieve a really good performance. And another thing is the designs we have, the interleavers are made random, but they're produced by algebraic calculations. So you only have to save a few parameters to generate random interleavers, which is also critical, because if you have to save a low random interleaver in your chip, it's very difficult. It takes a lot of memory. So that's where after that, this insights actually, the Turbocode actually took us in another domain. So people started to realize, okay, we achieved Shannon capacity, we can do better communications. In particular, I was working with satellite communication research group. So in the sense, we have a lot of problem unsolved at that point for deep space communications. So we were able to redefine a lot of the problem. So for example, bandwidth and latency constrained communications with various different corrupting noise. We could be able to use this principle to come up with new codes and decoders. And then search and rescue satellite, which is one of the critical satellite. As a federal employee, that was really important for us to come up with really, really good coding, decoding systems to save more people. So we were able to redefine and propose different standards for SARSAT. And then satellite-aided automated ship detection, the ships are detected using coding as well, so we were able to do that. The other thing is, as I was in Canada, and northern part of the territory of the Canada is far away, they don't have good facilities, so we were able to do some telemedicine and so on using better coding. So there was a lot of rewarding experience I received based on this along the digital revolution. And coming back to wireless communications, so this is where we were at the point. So it's like a fraction of a megabits per second, and we went to a few megabits per second, but that wasn't enough because the 3G, the internet was starting to come, people started to get more and more interested, so there should have been more data rate at the point. So there is another invention happened along with the Turbocodes. That's called MIMO Communication. So until say 1995 or so, people thought that in a spectrum, in a time, we can only have one electromagnetic signals. So if you have two electromagnetic signals, we thought that they're going to interfere, they're going to collide, and then we don't get anything out of it. But in 1995, something called multiple input, multiple output communication was invented, again in Crawford Hill Lab at Bell Labs. Actually, what they showed is you can actually do, it's like a vector channel model, and the multiple input, multiple output, each of them transmitting different data streams, but it goes through a rich channel matrix rather than just viewing as a single channel. Now it became a matrix channel, and then they were able to plug that matrix channel again in Shannon's formula, so it worked. Shannon's invention worked at that point as well, and that they were able to prove that when we have multiple antennas in transmitting and receiving end, we can actually have parallel signals. Okay, so the conventional view was we can only have one signal in a spectrum, but in 1996 they proved that actually we can have multiple signals in the same spectrum at the same time. So that actually was a huge growth because you can actually have linear growth in the data rate. So that was the needing requirement in the wireless communication research at that point. So we wanted to have more and more data rate. So in that sense, what happened is capacity, say if I have only one transmit, one receive, I could only get 3 bits per second per hertz. If I have 16 transmit and 16 receive antenna, I can have 48 bits per second data rate, okay, without increasing the bandwidth or power. So that's a huge growth. But the problem is now we are back to the square one in the sense we have to now design codes for multiple antennas. So Shannon's theorem didn't support that because Shannon said a single link you can actually do random long codes to achieve that capacity, but now we ended up with even difficult problem, although we know a lot of capacity. So at this point, just to remind the disclaimer by Galileo Marconi, which he predicted that it is dangerous to put limits on wireless. So indeed, it was proved at the point that you can actually put more and more antennas to increase the capacity in the wireless channel. So the Bell Labs didn't stop at that point. They actually built multiple input, multiple output systems, and they were trying to prove in practice. I was lucky enough to be there at that time, so I was in the right place and right time to visit them as an intern student for my PhD, and I was able to participate in the channel measurements as well for them. And indeed, they come up with some sort of transmitter receiver. So there's some coding scheme for Spacetime and the receiver scheme for multiple receiver. And so you can imagine that because now the problem complexity is very high because you need to have multiple streams going and multiple receivers receiving it. So it is much more complex than the conventional single transmit, single receive. So actually, they were able to prove using their transmitter-receiver system that at that time for one of the standards here was receiving 3.2 bits per second per hertz in a certain bandwidth. Using the same bandwidth and the same system, using 8 transmit antennas and 16 receive antennas, or 16 or 12, they will actually achieve 8 times capacity, 25.92 bits per second per hertz. This slide is from them. This is the first slide they have trying to prove the capacity growth using multiple antennas. So this is one of the historical results. We measured the received signal because multiple signals, many signals coming, so they kind of interfere that you receive as a cloud. But then when you decode, you can actually decode and get the constellation right. So that was, and then they were going into proving the capacity limits. And this is the possible capacity that we can achieve. Again, this plot, say you see the rates per bits per second per hertz in the axis. So the more higher the better. So 90 means 90 bits per second per hertz. And this is some sort of outage probability calculation. So, and the conventional was somewhere in 10 bits per second right here. And the achievable rate for the system they used is like here in the 80s. And what they were able to achieve using their system was somewhere here. So this is a theoretical performance. I mean, even in practice, they only achieve half of it. That's when they measure and do the actual receivers. So there is a big gap to fill. So that was a challenge they were actually asking for us to do as an intern student. So in that time, I decided to, I had the experience with the turbo coding, and so I thought of doing, why not we try the turbo principle in the spacetime manner? So I just come up with something called random layered spacetime coding, and eventually we named this as a turbo spacetime coding in the sense like, you know, rather than you do, but I had to say that the other end, people who started to design algebraic spacetime coding already at the time. So I thought I'll do follow the turbo principle, and I do some random coding. And so I did some random coding with the belief that I can also decode them with a very simple one-dimensional receiver. So I don't have to have the exponential complexity maximum likelihood receiver. So in that sense, there was something called Turbo Blast that we kind of invented, and it worked really well. So it has the same principle. It has an iterative receiver and some sort of random layered spacetime coding. So we use the same principle, something we call extrinsic information. You can compare it with the exhaust in the turbo machines. So that we can pass this information back and forth, we can actually achieve a really good capacity. So I tested, I was lucky enough because I was there, I was able to test my algorithm in the real testbed. So that gives nearly in the Indo environment, 90% of the MIMO capacity. So I could achieve my, using my receiver 90%, where the other receiver was achieving 70%. And similarly for outdoor measurements, I could actually, so I could get 80% of my MIMO capacity, where the receiver was 60% of the capacity. So that became very popular at that point, and Samsung, Huawei, and all those people were started to use, and it became as a research topic, turbo MIMO. So there's a huge amount of work done in that direction later on. So after that, I was, we were trying to, at that point, MIMO is important. But at that point, critically important thing was uplink communication. So typically, any time, any frequency, you can only put one user in the uplink. So the user communicated to base station. Okay. So we use the same principle, whether we can actually use multiple users communicating the base station at the same time and the same frequency, but we can put multiple antennas at the base station, which is much more logical because they can put multiple antenna in the base station, but it's very difficult to put multiple antenna in a receiver terminal. So here is a demo in the sense I have so various different signals. I'm going to reduce the sound because it was too high when I was testing. So it actually, say voice signal, different signal. So that's a different signal. That's a different signal. So we can put different signal and then we transmit over the channel without any special coding. Like in the conventionally they used in the 3G early days, they used CDMA. So there's something called code division multiplexers, but the data rate is very low. It never achieved the capacity. So all of these are received together as noise, and then we put together, we design the coding for single users and the receivers. We can actually decode them. So that was some of the earlier work in the multi-user communication development. So what we used is turbo decoding principle. In other way, it's called iterative decoder. In the sense, you do slowly decode it. You peel a bit of information at a time. So here I would like to demonstrate that. So these are the received noisy signal. So this is the first iteration of my peeling receiver. So a little bit of information, a lot of noise there. And the iteration 2, you get a slightly better signal. So that's the 5th iteration. It's more or less good, but when you do a bit further, they'll become really good. So that's the idea of these multi-user communications. So, and the other thing with the CRC, Communication Research Center, and after the PhD, I went back to CRC. At the time, because I have this MIMO knowledge, one of the questions put it on me was whether we can use MIMO sort of principle to SATCOM. So we were the first one to actually propose a dual polarized, because MIMO, SAT is very far away. So it's very difficult to put MIMO directly. But you can actually use different domain. Like we use, rather than using space domain, we use polarization domain, and then we can actually prove the capacity increase using theoretical channel models. So it's one of the first work. But surprisingly, after 10 years, when I'm here at Harriet, ESA did measurement for dual polarized channel. It picked up after 10 years. It was like, didn't pick up for a while, because it has to be measured to prove, but ESA actually measured, and I was lucky enough to send my PhD student to work with them and to actually calculate and prove the doubling the capacity for satellite communication using dual polarized. So all this work led to a lot of rewards and awards for me. Then I was really lucky to be at the right place at the right time. Actually, also was acknowledged because I was working for the federal government. I was also received acknowledgement from the parliament and the prime minister at the time, Chrétien. And then in the UK, so the 4th generation, whatever I talked about now, it's all about the 4th generation communication. So we moved on to the 5G now. The vision for 5G started earlier. So the 2020 is probably the starting point for 5G, so it's not yet, but some of the aspects already started showing up. So at present, what we are working is the 5G communication. So there are 3 different things proposed in 5G. One other thing is we want to enhance the mobile broadband data rate further, because people wanted to have no patience. They wanted to have very high speed video. They wanted to do games and also watch real-time sports and so on. So there is a real critical need to enhance the mobile broadband. And on the other end, one of the other things we are talking about, Internet of Things, so device-to-device communication. So I'm just going to briefly tell what we are doing in these domains. So network is changing, because earlier days it's for voice communication the networks planned, but eventually it become now video. Video is the critical application. It's taking up a lot of the spectrum. So the spectrum is already in deficit. It's used. So the spectrum efficiency continue to be one of the key things. And the 5th generation, the governments are now agreed to include millimeter waves to enhance data rate. So millimeter wave is very new spectrum for communication, so we need to understand that. And the other thing is energy efficiency, because most of the cost for the telecommunication operators and also people who are paying for it is used for energy. And it is also critical for global warming and so on, so how we do it. And the other thing is, if you want to use device-to-device communications, we need to have network efficiency, because there are some of the applications like autonomous car, remote surgery and so on has to be done on time. So the network has to be efficient, and also very low latency communication. So there are fundamental delays that we cannot change because it has to travel in the speed of light and come back. So that we cannot change, but how we can change low latency communications. And the other thing is, because people, we are the one using communication all those years, so we have the intelligence. So we can actually, when we receive a signal, we know that is it noise, or it's rubbish, or it's a real signal. But the devices, if they don't have intelligence, they can confuse. They can get confused, so they need to have intelligence. So there's a lot of different factors coming in the 5G that we are working on. So a lot of the work done and during the past 10 years in my group. So one of the things is we were experts in MIMO, so we went into massive MIMO in the sense, rather than having tens of antennas, if you have thousands of antennas or hundreds of antennas, we can actually increase the cell capacity. We can serve more users. And the other thing is heterogeneous networks. So in the sense, the millimeter wave, if you bring us extra spectrum, it's not going to replace the microwave. It's going to be an addition to microwave. So how we can coexist, how we can use the millimeter wave more effectively. The other thing is cloud edge computing and caching. This is also common for people and devices in the sense a lot of social media videos are downloaded. How do we actually manage the unnecessary traffic flow? So if somebody is downloading a popular video, whether we can cache it somewhere, but we need to have intelligence to do that. So that, and the other thing is, can we double the spectrum by using full duplex system? Because the current system uses half duplex in the sense any antenna will transmit or receive. That's the only thing it can do. Whether we can make an antenna to transmit and receive, it's almost like you talk and listen. It's a very difficult thing to do. So we all these things we also do test bed, and we're trying to demonstrate all the ideas as well. So these are the work we've been doing. And another domain we moved on is the artificial intelligence. So I just put this slide to show how much the artificial intelligence is growing. It's grown significantly. There's so many algorithms. So our challenge was to see whether we can actually use AI in communication system design. In the sense, that's the top one is the communication problem given by Shannon. So we have a conventional way of doing it. Whether we can remodel this using artificial intelligence. In the sense, it makes sense because a lot of the wireless communications problems, we don't know the capacity because Shannon didn't say how we can actually calculate capacity for interference channel, multi-user channel, relay network, and so on. There's so many coming in. So we were trying to use the existing theorem and existing coding and just survive, but we never did optimal way of encoding and decoding. So in that sense, we will started to do some work in the multi-user communication. In the sense, it's called coded modulation that we designed. So it's a conventional way of doing coded modulation. It's also differential coded modulation. In the sense, it's 14 dimension. I have my PhD student did it for me for projected on 2D, all 14 dimensions. So the conventional way is very simple. But if you do use data and learn using machine learning, we get very complex modulation scheme. But the advantage is we can actually get significant power gain because it's the machine can actually identify and optimize it. The relay network, it's also an unsolved problem, two-way relay network in the sense we can't communicate directly, so we had to communicate through a relay. So what we do is we need to communicate at the same time through a relay. So it's a difficult problem again. There's no optimal solution. So we tried, rather than using the conventional modulation way, this is conventional, we designed much very complex. We've seen a lot of gains. The added advantage is it's not only doing coding modulation together, eventually we realized that it's also do some sort of security. Okay. So there are a lot of advantages doing that. And then the other work we've been doing is modeling channel for millimeter waves. So as I said, millimeter wave is a new frequency domain that's going to be used in the future. So with the Bell Labs, they were measuring 28 gigahertz. As I was with the labs to do the MIMO measurement, one of my PhD students was able to go and help them the measurement, and he was also looking into how we can model this millimeter wave channel using machine learning. The advantage of this is conventional wave wouldn't consider objects in between transmitter and receiver. But knowing the objects, we can actually do better with AI. So this is very critical for millimeter wave, because a millimeter wave is very small wavelength waves, can be absorbed by objects very easily. So that's another direction we are doing. Another final thing I want to tell about is something exciting about IoT device-based hearing and visual aid. So again, I come back to the history. It's Alexander Graham Bell. He's again from Edinburgh. He's a Scottish-born scientist, and along with his wife again, Mabel Bell. So she was deaf from 5 years old. So here his intention was to invent a hearing aid, but he invented telephone hearing aid. And also he's the founder, he and his wife are the founders of AT&T Bell Labs, so it's connecting the story back there. And so the hearing aid has 150 years of history, but the problem is, again, the hearing aid, the problem is not solved, because people trying to put very small device, you cannot put too much computational power, you can't put too much sensors. So it's a stigma. So you had to make a very small device solving one of the most powerful organ of a human being, like hearing. So it is not solved, because we were like stuck with that idea. So it is also a responsible innovation, in the sense there is not enough supply for need, and the uptake also very low, because the hearing aid people getting is not satisfying them. It's very difficult to satisfy people, because the hearing aid is a very personal issue, and it can be ranging from various levels of hearing aid. So the idea is, whether can we make the hearing aid as an IoT device? So just taking the stigma of using small hearing aid, can we put a glass and a hearing aid with more sensors, sending audio-visual information to cloud, because this devices cannot do much more computation, and 2 ears has to communicate as well. So 2 hearing aid has to communicate that. Throwing the data to cloud or a device and then cloud, do the computation up, and then return a clean signal. I don't know whether it's possible, but it brings a lot of challenges for us, because it has to be trustable, reliable, interoperable, privacy, security, low latency, and intelligence. All of this has to be solved. But as a researcher, it's very exciting for me to look at it. And further to build on, so this 5G brings this IoT domain, and there are a lot of responsible research can be done, and innovation can be done for people who needing real support, like artificial limbs, whether they can be made as an IoT device, in the sense they can be much more intelligent, they can talk to other devices and bring more intelligent and upgradable, so the hardware can be fixed and the software can be used to upgrade it to more and more personalized manner. So there is so much of research can be done in this direction in the 5G, to improve the quality of life for people who cannot rely on their vision, sense of hearing, and mobility. So this is one of the directions. So autonomous cars, another direction, telesurgery is another direction. So it is like invention come before research, in the sense there's so much of application that need revisiting. So with that, I'm closing my talk, just reminding everybody that it's dangerous to put limits on wireless, the disclaimer by Galileo Marconi. Thank you very much for